All right, guys, we are on to part B, where we're actually going to be doing the hard part and doing the calculations. So, last time you learned what ANOVA was and why it works. You understand that it's a test comparing signal to noise, the between group variance relative to the within group variance. You know that large F means the groups differ and a small f means that they don't. But you don't know how to actually calculate an F statistic from raw data. So that's what today is about. Here's the good news. The math is not hard. There are no concepts here that are harder than anything you've already done. The challenge is not difficulty, it's organization. You're going to compute 7 different values in sequence, each building on the one before. It's like following a recipe. You need to keep track of what you've done, check your work at each step, and not get lost in the middle. And here's the better news. By the end of this lecture, you should be able to do this. And what you can do, if you can do ANOVA by hand, software like SPSS or Jamovi becomes easier, becomes less magical, because you'll understand what it's actually calculating. You'll be able to catch errors better and so on. So let me recap one thing from last lecture before we dive in. So you hopefully watched the video on degrees of freedom. That is available, so I'm just reminding you. So degrees of freedom between groups, the formula is G, the number of groups, minus 1, just like n minus 1 with the regular, when you're not doing multiple groups, only doing 2 groups. And then the degrees of freedom within is slightly different, where you have the number of observations, total number of observations minus how many groups. So G is the number of groups. After estimating each group's mean, you'll have n minus groups, independent pieces of information left. So that's your degrees of freedom. If that's confusing, go back to the degrees of freedom video. So just a quick example, we have 3 groups and we have, let's say we have 18 total observations. Then you're going to have the DF, that's a D, DF, I'm just going to write between, is 3 minus 1, which is 2, and the DF within is 18 total observations minus 3 groups is 15. And then, of course, hopefully you remember how to write that out. But anyhow, we'll get to it and we'll do all that. All right, so part 1. So before you compute a single sum of squares, you have to do 3 things, and this is non-negotiable. Most calculation errors happen because students skip this step and they jump straight to the math, okay? So these are like the 3 prior steps. So this is step 0A, okay? So step 0A is state your hypothesis. State your hypothesis. So your null hypothesis, okay, is mu1 is equal to mu2, which is equal to mu3, or however many groups you have. All 3 groups have equal population means. There's no difference in the outcome across groups, okay? And then the alternative hypothesis is at least 1 is different, okay? So you have mu1, and there's going to be a difference in maybe 1 or maybe all of them, okay? At least 1 is going to be not equal. You don't know which group or in what direction, only that something is different. And then our alpha, you have to figure out what your alpha, but in this class, it's always going to equal 0.05. Always, okay? In this class, no exceptions. Just make it easy. And then step 0B, you're going to calculate your degrees of freedom, okay? So we'll just figure that out. So you've got your DF between and your DF within, and those are going to be essential for everything that follows. And then step 0C is going to be find your critical value. Okay, so you should start out with these. Go to the F table, find the column for the degrees of freedom between, and find the row for the degrees of freedom within, the numerator and the denominator. Read the cell where they intersect. That is your F critical value. So, then write it down, and do this ahead of time. You need to know your finish line before you start running, and you're going to do better. Don't start calculating the sum of squares until you've done these 3 things. They anchor the entire analysis. If you if you don't know where you're going, it doesn't matter how fast you're running. All right, so then the real setup, the real 7-step sequence, okay? So I'm going to show you the full sequence of calculations. There are 7 steps. When you see them all at once, it looks terrible, I know. The formulas seem to come from nowhere. There's Greek letters, there's algebra, but here's what I want you to notice. Each formula builds on the one before it. There's a logical sequence. Take it one step at a time and you won't get lost. Also, this is probably the most calculation-heavy test that we do in this course. The math itself is not hard. What's hard is keeping track of everything. So take your time. Give yourself space on the paper. Some of you guys just put so much onto one piece of paper, and it gives me a headache to try to read it. Use lots of paper. It's cheap nowadays. It's not the medieval period where we're writing on leather or whatever. Use paper. Use a calculator. That's totally fine. Check your work at each step, okay? So there are 7 steps. Okay, step 1 is the grand mean. This is just the mean of all the groups, okay? It's X bar, double bar, okay? So you add all the scores from all the groups, you divide by the total number of groups, by n, okay? Step 2 is you're going to calculate the total variance, the SS total, okay? The sum of squares total. For every individual score, you're going to take the score, subtract the grand mean, square it, sum all of them up, just like you've done with all the other tests. It's no different. It's just now you're doing it with a bigger group, okay? So remember x minus mu, you're doing the same exact thing. You're just finding that gap, that raw score gap between the two. What's the difference between what I observed and what I expected, okay? And then you'll do the SS within. So for every score, subtract its own group mean, square it, and sum across all the scores, okay? And then SS between, so the SS total minus the SS within. Once you have the first two, this is just subtraction, okay? It's an easy step. You're just finding the difference between the total. You've already found the within. What's left over is the between. Then you're going to do the mean squares, okay? The mean square between, and this is the SS between divided by the degrees of freedom between, okay? And then the MS within. I know this is getting intimidating now, right? And that's the SS within divided by the degrees of freedom within, okay? And then you'll get to your lovely F score, which is MS between divided by MS within, okay? Steps 2 and 3 are where most of the work is. Once you have those, steps 4 through 7 are just quick arithmetic. Every formula builds on the previous one. That's what makes it manageable. I know it looks scary, but it's not. Just stick with me. We'll get through it, okay? That's why I picked an easy example for us to start. Okay, so we're going to work through a full ANOVA calculation using the Barbary Pirates data, and this time it's using real data. We actually know how much everything was, how much we paid or were paid or whatever. So this is the kind of problem that you'll see in real life, and this is also the kind of ANOVA problem that you might see on a quiz. Okay, so we have the data. Now we have to start with our setup, our pre-steps. Okay, so step 0A. That's our hypotheses. So we have our null hypothesis that the means are all equal. There's no difference in the appeasement, the threatening with the war in the Navy, or the Decatur go in and shoot them up, bang, bang version, okay? And then hypothesis 1 is that something, one or more groups do not equal the others in their average, in their mean. And of course, we are going to use an alpha of 0.05 because that's just what we're doing in this class. Okay, so pre-step B, we are going to determine our degrees of freedom and the degrees of freedom between and degrees of freedom within. So degrees of freedom between, pause it and see if you can remember the formula yourself. Pause it, give it a try. You'll remember this so much better if you actually try. Okay? Even if you get it wrong, it'll still stick in your mind better. So that is the number of groups minus 1. That is the between formula. And in this case, we have 3 different groups, our 3 economic strategies. Minus 1 equals 2. Our degrees of freedom between is 2. Degrees of freedom within, again, pause it, see if you can figure this out on your own, see if you can remember the formula. So degrees of freedom within is the number of observations minus the number of groups. And in this case, we actually, the real life data, we have 17. We threw one out as an outlier. I'll talk about that later and why we did that. So we're going to have 16 total observations, 16 years of data minus 3 groups. That leaves us with 13 degrees of freedom, 13 variables that are not accounted for. Step 0C, we're going to find our critical value. Okay, so go to your F table and then you will go to column 2, row 16, where they meet is going to be, why do I have 16? It should be 13. Let me double check this. Yeah, I don't know why I have that wrong in my notes, but anyhow, it's column 2, row 13. Hopefully I have my F value right, because since Canvas is shut down right now, I don't have access to the F table that we're using, but we're just going to go with this, okay? So F critical equals 3.81. Fingers crossed that's actually correct. That's what I have in my notes, so hopefully we're right. If not, I'll post on here what the correct critical value is. Make sure that you guys see that. So anyhow, that is our cutoff, right, for our rejection region. Anything above here, we reject the null, and that line equals 3.81. So we have to find an F score, an F ratio that is above 3.81 in order to reject our null hypothesis. Okay. So now we go on to our first actual step, which is finding the grand mean, which is easy. It's just like finding any other mean, okay? So the grand mean, x double bar, is just the sum of x over n, okay? It's the average of all the scores, ignoring which group it is. We're just adding them all up all together. So if we, so we have the data here, okay? So you can see the scores of 56,000, 107,000, 22,000, 40,000, 22,000, 23,000, a bunch of 22,000s, 82,000. You add all of those up, okay? So we have 56 plus 107 plus 20 plus 40 plus 22 plus 23 plus 22 plus 22 plus 22 plus 22 plus 82. Maybe I should be doing this on my calculator. It would be a lot easier. So let me do that. So we have our scores, which is the amount of money in thousands that was paid. So we have 56,000 plus 107,000 plus 22 plus 40 plus 22 plus 23 plus 22 plus 22 plus 22 plus 22 plus 82 minus 80, because we got paid back with Decatur, and plus nothing else because it's all zeros, okay? So that gives us a grand total of 360 divided by 16 total. So our average, our grand mean is 22 and a half. Okay, so you sum all 16 scores, divide by n, you have a grand mean of 22 and a half. So step 2, we are now going to calculate our SS total, our variance total, okay? And the formula for SS total is the sum of So for every individual score, you're going to subtract the grand mean, okay? Because we want to see the difference between the value and the grand mean. This should be very familiar because this is exactly what you did with t-scores, but instead of the mu, or x bar, we're using the grand mean. So x minus x double bar, the grand mean, and then we have to square it to get rid of the negatives, and then we'll add it all up. Okay, it's the same exact formula that you did before. We're just changing the labels because this is now multiple groups instead of just one group. Then we sum it all up, right? Because that represents all the variability in the entire data set. Okay, so let's look back at the table. So we have our scores here, right? And we know our grand mean is 22.5, right? 22.5. We'll write it here, okay? X bar bar equals 22.5. Okay, so write that down where it's easy to see. So then we're just going to take every value. I'm not going to do all of them, but 56, 107, 22, 40, 22, 23, and etc. And then we're going to minus the grand mean instead of just the group mean, because now we're looking at groups instead of a group. So that would be 22.5 for each one. 22 minus 22.5, 40 minus 22.5, 22 minus 22.5, 23 minus 22.5, etc. What does that equal? 56 minus 22.5 is 33.5. 107 minus 22.5 is 84.5. 22 minus 22.5 is negative 0.5. 40 minus 22.5 is 17.5. 22 minus 22.5 is negative 5. 23 minus 22.5 is positive 5. Okay, and again, you just keep going down. And then you have to square all of these, right, to get rid of the negatives. Okay. I pretend those are equal signs because I'm tired of drawing them out. So the squared score, 33.5 squared is 1,222.25. 84.5 squared is 7,140.25. Negative 0.5 squared is positive 0.25, etc. Okay, and then you're going to sum all of those up. Okay, so if we look at each group, so we have the appeasement group, which is what we were just working on, Adam's appeasement group. The sum of squared total, or the sum of squared, is 8,569.5. For Jefferson's group, the war group, that was 3,541.25. And for Decatur's don't negotiate with terrorist groups, it was 12,531.25. Then you sum all of those up, okay? So the sum total is 24,642, okay? So double check this. Does this make sense? The data spreads from negative 80 to 107. That's a lot of variability. So a large sum of squared deviations is exactly what we would expect. 24,642 tracks. Also notice the Decatur group contributes the most to the SS total. Okay, you would think with all those zeros that would be close to zero, but that's not the way it works, because so for Decatur's group you have 0 minus 22.5, which equals negative 22.5. That's going to be a lot of large numbers. So zeros actually add a lot to the variability. Okay, because that's very far away from the average. At least 0 in this case. Maybe in another case it wouldn't. If the group average is close to 0, then obviously that's not a lot of variability. But 0 is more variability than than 22 is. Okay? So it adds a lot to the variability. So just over half of it, really. It's 12,531. And nearly all of that comes from a single observation, the negative 80 reparations payment in 1815. Which is 102.5 units away from the grand mean. So that was a lot of variation. So even though 4 of the 5 Decatur scores are 0, that one extreme value pulls really hard, which is why we threw one of the values out that I'll talk about later, an outlier. So step 3, we are going to calculate the SS within. So we did the SS total, then now we do the SS within. Okay, so for each score, you're going to subtract the mean of its own group, not the grand mean, but the group mean, then square it, then sum across all the scores in each group. So this is the variability within each group. This is the noise. This is the, the scores bounce around within their group. Even if the group mean is constant, within each group, there could be a lot of variability. So we need to know how much noise there is within the groups before we can compare the groups. Okay, so this is the heavy computational step. So take your time, and I'm going to show it group by group. Okay, so the appeasement group, if you add all these scores up, the group mean, just the X bar, not X bar bar, is 45. Okay, I'll just do that work for you. Okay, so then we're going to take the scores, 107, 22, 40, 22, 23, and then we're minusing the group mean, okay, the 45. So not the X bar bar, which was 22 and a half. When we're doing within, we're just focusing within one group. So we're just looking at that group mean. How much variance is there within the group, okay? So 7 minus 45, 22 minus 45, 40 minus 45, 22 minus 45, 23 minus 45. And then you'll get is 62, negative 23, negative 5, okay, so on and so forth. And then you square all of those. Okay, this should be very familiar to you. You've done a lot of this already. Then once you square all of that, you're gonna, then you have, let's see, 62 squared is 3,844. So, you add all those up and then you sum it, right? And so the sum for the appeasement group is 5,532. Then you're going to do it for the next group. Okay, so you find the group average, the group mean, that's 34. Then you want to see what is the gap, what's the deviation from each score to the mean. Okay, you 22 minus 34, that equals negative 12. You square it to 144. You do that over and over again. You add it all up. And for that group, you've got 2,000, for the Jefferson group, 2,880. Then you're going to do the same thing for the next group. Okay. This is all easy. You've done all this before, okay? So negative 80, for this group, the average is negative 16. So score 1 is negative 80, so negative 80 minus negative 16, which is actually the minus, double minus cancel themselves out and becomes a plus. So negative 80 plus 16 is negative 64. Square it, 4,096. Do that over and over again. The rest of them all square out to 256. Add them all together. And for the Decatur group, you have 5,120, okay? It's a lot of work, but it's easy. You've done all this before, so this is not going to be hard, okay? It's just a lot of work, that's all. Okay. So then you add all those up, right? You're gonna sum the squares. That's the SS, sum the squares. So you square everything, sum it all up. Then you want the SS total. Okay, so if you add all of this up, it equals out to 13,532. Step 4, sum of squares between. What is the formula for that? Well, that one's easy, okay? This is just simple subtraction. You've already done all the heavy lifting. SS between is where you get to take a little bit of break. Okay, you have the SS total. Okay, we've already calculated that. And then you just subtract the SS within from that, and that equals the between, okay? So if you go back to step 2 is the SS total, which is right here, 24,642. 2,642 minus the within, which was step 3, and that is 13,532. 13,532. That equals out to 11,110. Okay? So 11,110, that's pretty close. Okay? The between is pretty close to the within. So the signal leads the noise, okay, but not by a landslide. Okay, so this is going to give us a moderate F statistic. Whether it clears the critical value or not is what we're about to find out. On to step 5, we're almost done. Okay, we're going to calculate the mean square between, because remember we have to standardize those buckets. Okay, so that the buckets have we're putting the same label on the buckets so that they have the same unit of measurement, basically. We're standardizing it. Okay, so MS, the mean squares between, you're going to take the sum of squares between and standardize them by dividing by the degrees of freedom between. Okay. So we're taking the mean squares is just the sum of the squares divided by degrees of freedom. And this standardizes the sum of squares so we can compare things that have different degrees of freedom. Okay, because if things have different degrees of freedom, it turns them into apples and oranges. So we have to standardize the degrees of freedom. It converts a total into an average, which is, of course, what the mean in mean squares means. And why do we need to standardize? Because a larger sum of squares between, SS between, doesn't automatically mean a stronger effect. A study with more groups will accumulate more squared deviations just by having more comparisons to make. So dividing by degrees of freedom puts everything on the same scale regardless of how many groups you have. Okay. So in this analysis, degrees of freedom between is, remember the formula, okay, test yourself, pause it. What's the formula? G minus 1. So we have 3 groups, minus 1 equals 2. We lose 1 degree of freedom because once you know 2 group means and the grand mean, the third group mean is determined. So the MS between is the sum of squares between divided by the degrees of freedom between. So we know the sum of squares between was 11,110, right? So 11,110 divided by the degrees of freedom between, we just calculated, that is 2. So the mean of squares that are between is 5,555. Okay, easy peasy. So your estimate of the between group variance, the signal, okay, easy. So in step 6, we calculate the noise estimate. Let's just do it on the same thing here. Step 6 is the MS within, the mean of squares within, the within bucket rather than the between bucket. And this is the same exact thing, okay? Easy. The sum of squares within divided by the degrees of freedom within, which we've already figured out. Try to remember the formula, degrees of freedom within. The formula is N minus G, okay? So same as operation 5, you divide a sum of squares by its degrees of freedom. And this time we're standardizing the within group variability to get our error variance estimate, okay? So N minus G, we have 16 years of data minus 3 groups, that equals 13, okay? 13. And so we lose 1 degree of freedom per group, because once you know all but one score in a group and that group's mean, the last score is determined, okay? So within 3 groups, that's 3 lost degrees of freedom, which is exactly what N minus G gives us. So that's the denominator of your F ratio. It represents the average amount. I forgot to, let's do this within. Okay, within was 13,532. Okay, I'm going on without finishing the calculations. 13,532 divided by 13 is 1,041. So that is your MS within. Okay, your MS within is 1,041. This is the denominator of your F ratio, the one that goes on the bottom. It represents the average amount of variability that you would expect to see within groups just from random noise. Okay, that is the noise number. It's the baseline against which you're going to compare your between group signal to see if it's large enough. If MS within is large, your groups are very messy internally, and it's going to take a bigger between group difference to stand out. Okay, so if you're looking at your F ratio, of your signal over noise. MS within is the noise, okay? It's the denominator. So the noise floor is 1041. So in step 7, we're going to put that against the MS between of 5,555, okay? So, which we'll just do right now. Simple piece of cake. So we just take 5,055 and we put it on the top, okay? So step 7, calculate the F ratio. So F equals MS between the signal over MS within the noise, okay? Signal over noise. So again, this is the moment, this is the whole point of the last 6 steps. So if you remember the between, okay, go back to here, got the between and the within. So 5,555 over, what was it, 1,041. Okay, that is your F ratio, and then of course divide it out, and now you have an F of 5.34. Okay, so 5,555 divided by 1,041, 5.34. We've gotten there. Whew. Stresses me out just like it stresses you guys out, okay? So that is the correct calculation, which means that the signal it's there, okay? It's not 1, right? So if you look at the distribution chart, right, 1 is way over here. If it's 1 or close to 1 or 0, then, well, not 0, close to 1, then the signal doesn't outweigh the noise. But this is 5.34. Now, is it enough to get past the critical value? Well, we have to remember what our critical value was, okay? So now we get to the decision stage. So you draw out the distribution. Okay, now we're in decision stage. Draw out the distribution. We have our hypothesis rejection region and our hypothesis retention region. What was our critical value? Our critical value, if you remember, was 3.68. So our F score is way up here, 5.34. It's really messy, but it's there, 5.34. So that is in the rejection region, obviously. So yay, we get to reject the null hypothesis, okay? That was what we said. If our obtained F exceeds the critical value, we reject the null hypothesis, okay? So awesome. So what does this mean? It means that the 3 strategies produce significantly different costs to America, which I don't think surprises you, okay? Like I said, I chose a very obvious example. You could tell from the beginning, but sometimes you're not going to be able to tell. And we're going to do another example where it's much more difficult to tell. But in this one is very, very clear, which you can see from such a large F, okay? That is a large F ratio, that it was very clear, cut and dry, that not negotiating with terrorists saves us money, okay? It was much better for us, at least with the Barbary pirates. Whether that generalizes to other terrorists or not, with Barbary pirates and paying tribute, it was way cheaper for us to not pay tribute. Now, of course, that doesn't take into account the cost of waging war and all that good stuff. I kept it simple for you guys. So when your obtained F is this extreme, the p-value is essentially 0. In fact, any statistics software would probably report this as p is less than 0.01. It's a pretty significant F value. So it may not be 0.05 or 0.01. It could be 0.001 if the F ratio is high enough. I'm not sure what it is for this one. It might just report it as p is less than 0.01 instead of 0.05, but that's pretty significant. So that means like that it would at least beat the alpha of 1%. There's a 1% chance of an error of it being that high, would be my guess, if not 0.001. Okay, so when you report ANOVA results in research, you use a standard format, and here's what it would look like. You have, you're going to put your between groups and within groups, and say what those are. And then, so the between groups is your strategy, within groups is error. You're going to report your degrees of freedom. You're going to report your sum of squares, your mean squares, your F ratio, your p value or alpha value, and then your effect size, which we're going to talk about. Okay, and then the totals for degrees of freedom and sum of squares. And then the way you write it out with APA format would be something like, a one-way ANOVA revealed a significant effect of diplomatic strategy on annual payments to the Barbary states, with F213 equals 5.34, P value of less than 0.05, effect size 0.45, which I'm getting ahead of myself with that, but we will talk about that shortly. Okay, so let's talk about some mistakes. So before we finish, let me point out the errors that I see most often when students do ANOVA calculations. So mistake number one is confusing the grand mean with the group means. When you calculate SS total in step 2, you subtract the grand mean from each score, not the group mean, the grand mean. When you calculate SS within in step 3, you subtract the group mean from each score, not the grand mean, okay? The group mean. So this is the most common error. Double check yourself. Are you using the right mean at each step? You start with the grand and then you go to the group, okay? Mistake number 2 is forgetting to square. After you subtract, you must square. You have to get rid of those negatives every time. I've seen students calculate x minus m and then just add them all up without squaring. So if you don't square, negatives and positives cancel each other out and you'll get 0 or near 0, which is obviously wrong. Always square. Every deviation score squared. The third mistake is arithmetic errors in the heavy steps. So step 2 and 3 involve a lot of arithmetic. It's basic, easy stuff, but it's easy to make a calculator error when you're subtracting large numbers, squaring them, and adding them up across many scores, especially if you start getting tired. So use a spreadsheet, set up columns, score, grand mean, deviation from grand mean, squared, group mean, deviation from group mean, all of that good stuff. Set it all up so that it's easy to see, so it prevents errors and makes your work visible. Or at least if you're doing it handwritten, make columns, make yourself a paper spreadsheet. Okay. The fourth mistake is the wrong degrees of freedom. So double check degrees of freedom between is groups minus 1. How many groups do you have? Minus 1. And then degrees of freedom within is how many total observations minus how many groups you have. Okay. And the fifth mistake is forgetting the setup steps. So you'd be shocked how many students calculate all 7 steps, get an F value, and then don't know what to do with it because they never set up hypotheses or found their F critical value. So always do the 0 pre-step first. Okay, hypotheses, degrees of freedom, critical value before any calculation. All right, so we just ran that ANOVA, F equals 5.34, significant, P less than 0.05, that's your alpha. The 3 diplomatic strategies produced measurably different costs to American commerce, right? So what did we actually measure? We measured tribute payments, what the United States government paid to the Barbary states every year. And those numbers were real. They came from congressional records, $56,000 to Tripoli, $107,000 to Tunis, the $80,000 that we got back when Decatur extracted reparations. But here's the problem. Tribute payments are the treatment. They're what the policy was. Measuring tribute payments to see if the policies differed is like measuring the aspirin dose to see if the dosages are different. Like, of course they're different, right? That's the whole point of different doses. They're going to be different. You set them to be different. What you actually want to know is whether the patient got better. So what did getting better look like for American commerce in the Mediterranean? What we could measure it as is it means merchants could send ships. It means investors would back voyages. It means cargo could move between Philadelphia and like the city of Leghorn without someone betting their life savings on whether this particular voyage would end in a pirate's harbor and slavery in North Africa. Okay, so there's a more fundamental problem too. I tried to build this ANOVA using a bunch of different dependent variables, but one in particular was how many ships were seized. Count the ships taken in each policy era and see if the numbers differ across the groups. And the ANOVA kept coming back non-significant, F of near 1. No effect found every time. And at first that looks like a failure. And I was like, what's going on? It looks like the data doesn't support the historical story. But it's not a failure. It's the data telling you something that's true, that's valid about what it was actually like to operate in the Mediterranean without protection. So the reason the seizure count ANOVA fails is not that the groups are the same, it's that the within group variance in the unprotected era is enormous because piracy was predictable. Some years, nothing happened when we didn't have protection. One year, 11 ships were taken. That's not noise in the data. That's the actual nature of operating without protection. Catastrophic and random. You couldn't plan around it. You couldn't price it in. You couldn't tell your investors whether this would be a 0 year or an 11 ship year. That noise floor in the unprotected group was so high that even real differences between groups couldn't clear the critical value. So that's something to remember about ANOVAs is that they don't do well with variables that are messy. So if you have a noisy, messy variable like this one, you have to use a different statistic than ANOVA. So we're not going to do those statistics in this chapter because this is the ANOVA chapter, but we could run statistics on this. We would just have to use a different type of statistic. Okay, so there's different statistical tests for every type of variable, which is why you have to understand your variables so much, and you really have to spend a lot of time thinking about what exactly are we going to test. So the tribute system that Adams ran, paying off the pirates, it didn't just reduce seizures, which it did, okay, but it also reduced variance. So under appeasement, Adams paying off the pirates every year was zero. It was predictable, it was priceable. The uncertainty itself was the harm, and the treaty bought certainty, okay? So that changes what we need to measure. So what we need is a dependent variable that captures not just how bad things were, but how unpredictable they were. A variable that encodes the level of danger and the variability of that danger simultaneously. A variable that answers what did it cost American merchants to operate in the Mediterranean under each of these different policies. So there's only one variable that I could think of that does this, and fortunately we have primary sources of this data. Okay, so imagine you are a merchant in Philadelphia at 1797. You have a hold full of flour, of barrels of pickled fish, and you want to get it to Leghorn. That's the main trading port on the Tuscan coast of Italy. That's 6 weeks at sea through the Strait of Gibraltar into the Mediterranean Sea and straight past the Barbary coast. So you walk into an insurance office, and in Philadelphia on Walnut Street or whatever, and there's a broker there, and he pulls out a policy, an insurance policy for your voyage. He writes down the details of your voyage, the ship, the cargo, the route, the captain. Then he leaves it on his desk, and for the next several days, how this worked was wealthy men would come in and they'd read it, like merchants, retired sea captains, people who have traded in these waters for decades, who have friends who lost ships, who know the current political situation with Algiers and the other Barbary Coast states, and each one decides whether to write their name on that policy, to personally guarantee that if your ship gets taken, they'll pay for your cargo. Okay, that's the way insurance worked back then. It's the way some insurance still works today. So that the number that they settle on, the rate that they charge you for this insurance, is not one person's opinion. It's a bunch of very educated people's opinions on how dangerous this is. It's a market price. It's what you get when a room full of people who have money on the line and information about the world are forced to commit to a number. So it encodes everything they know, how often ships get taken, how bad it is when they do, how stable or chaotic the political situation is, whether the Dey of Algiers, the leader of Algiers, he was called a Dey, D-E-Y, is whether he's friendly or hostile this season, whether there's a navy in the Mediterranean to protect you or not. So this is what insurance companies look at. The rate equals expected loss plus variance, how variable it is. Okay, what we expect plus the variation of how bad it could be versus how good it could be. Okay, so a rate of like 27% means we think this route is so dangerous and so unpredictable that we need to charge you 27 cents on every dollar of cargo just to break even on the amount of risk that we're taking. So when they write that number, they're not just saying ships get taken. They're saying we don't know when ships get taken, and we're pricing the uncertainty. A rate of, let's say, 4% means that the route is pretty safe, okay? Atlantic level risk. It's a typical level of risk, and we'll take that bet all day, okay? That's a great rate. It's not very dangerous. So this is why insurance rates are the right dependent variable. They don't measure whether a policy happened. They measure what the people with money on the line thought the policy was worth. Okay? They're a market's collective judgment, updated in real time about how dangerous and unpredictable the Mediterranean had become under each diplomatic strategy. It's very, very similar to capitalism in general, right? We talked about that in the capitalism communism lecture, where it's the whole aggregate of all of the market variables coming together to form the price. Okay? So when the 1795 Algiers Treaty was signed, the insurance rates fell immediately. Not because seizures had fallen yet, but because the underwriters, the people who priced the insurance, believed that the route had become more predictable, it had become safer. They were pricing the treaty itself today, not last year's data. Okay, so when Decatur returned in 1815, rates fell to Atlantic peacetime levels within the year, not because they were waiting to see if the peace would hold, but because the threat was gone permanently at this point, and underwriters priced permanence differently from temporary arrangements. So think about what that means. Insurance rates encode something that tribute payments can't. Okay, the market's assessment of durability, of how long this situation would last. Paying the pirates and fighting them produced similar short-term rates, but the market could tell the difference between a policy that required an annual update, an annual renewal, and one that ended the threat for good. So that's not a conclusion I'm giving you, it's what the data says, and we'll see it when we run the post hoc test later. All right, so So let's be transparent about the source basis for the data we're about to use, because intellectual honesty is a value of our course, okay, value of statistics, or at least it should be. So these insurance rates are estimated from documented historical baselines. They're not raw numbers pulled from an archive. So let me tell you exactly what that means. So the INA, or the Insurance Company of North America archive data, the INA is the first joint stock marine insurance corporation in America. It was founded in 1792 by merchants in Philadelphia. Okay, so this paper that we're using by Kingston in 2007 uses their actual records to establish that peacetime Atlantic rates ran about 2.5% to 3% per voyage, and that wartime or high risk routes ran 20 to 30%. Another document we're going to use by author named Lambert, the Barbary Wars. Lambert documents Mediterranean specific rates somewhere 20 to 25% in the unprotected area, and significant reductions after the 1795 treaty, and then a return to Atlantic levels after Decatur's. Atlantic levels means like peacetime, when there's nothing bad happening. So this is just the baseline risk, like storms or whatever, but not pirates. So it returned to Atlantic levels after Decatur's 1815 campaign, which is around 3 to 4%. And then Stephen Girard, he was one of the wealthiest merchants in early America, and his own business archive records what underwriters called double risk on Mediterranean voyages between 1797 and 1804, which is roughly twice the Atlantic baseline, because the Barbary threat was still real even after our peace treaty. So from those documented baselines, the specific annual rates in our data set are period estimates. So they're constructed to be consistent with what sources say happened year by year as the political situation shifted. And they're very historically defensible. They're basically, what I'm saying is we've got good data. Okay. So they're not raw primary source records the way the tribute payment figures are. I'm using data from other historians, but okay, they're good. So this is what intellectual honesty looks like in practice: not hiding a limitation, not overstating what you have. The estimates are grounded, the sources are real, and the story they tell is accurate. Okay. So this is what you should always do with data. This is where I got it from. This is why it's good or not good. And then you proceed. Okay. So the data set. Okay. So our dependent variable is the insurance rates, the marine insurance rates. Remember, dependent means that this variable depends on another variable. So the insurance rates depended on the state of the Barbary Coast pirates, the state of the Mediterranean voyages. Okay. So that's our dependent variable. So we have 4 groups. Okay. We did 3 before, but we're going to do four groups this time, and I'll explain why. 4 groups with 5 observations each, so 20 total observations. Every group mean is a clean integer, which means that within group calculations are going to be very manageable. I rounded it off so that we didn't have decimals. Okay. So let's look at these groups. Okay. So we have group 1, which is the unprotected voyages. Okay. So this was during the period when we no longer had Britain's protection and we were kind of on our own. We hadn't done anything to deal with the Barbary Coast pirates yet, and they were just having a free-for-all. And then finally, Adams came along, and he appeased the pirates. He paid off the terrorists, okay? So the appeasement era. Group 3 is when Jefferson came along and said war. Okay, so appeasement, tribute. We paid tribute. Jefferson threatened war. And then instead of just threatening it, Decatur came along and kicked their butts. And then we had permanent peace. Okay. So what are the average policy rates? And remember, we're measuring this in percentage because it's percentage of a dollar. So in the unprotected era, we paid, if you were a merchant, you'd pay 27 cents on the dollar. So 27% of every dollar your voyage was worth. That's a lot of money. Okay. But it made sense because you were unprotected. It was a dangerous time period. In the appeasement tribute era, it went down to 11%. Still dangerous, but much less dangerous. Okay. Now with Jefferson threatening war, you think, okay, yeah, we're stronger. We're, scaring the pirates, so things are going to be easier. But it actually went up slightly to 13%. Now that's not a lot of difference. So even with war going on, the insurance rates were like basically the same as when we're paying tribute. But a little bit more dangerous because you also have the risk of maybe angering the pirates a little bit. But on the other hand, you have the American Navy actively in the Mediterranean Sea to protect merchant ships. So it's actually relatively the same. Okay, not really a significant difference. And then once we had peace with Decatur, it went down to regular risk of only 4%. Okay, so now what we have to do is calculate the grand total, the grand mean. Okay, so we've figured out all of our averages, and I just did this work for you, so you don't have to look through all of the data because that was a lot of effort for me to go through all those records and find these percentages for you. Okay, so for the grand mean, we're going to take all of the scores, okay, that added up to 27, and then we're going to calculate it all together. Okay, so you can see the rates of year 1 policy was 28%, year 2 was 25, year 3 was 27, year 4 was 30, year 5 was 25, and the average of those was 27. So we're going to add up all of those individual data points, okay, which, let's see, for the unprotected era, it's 135 total, plus 55 for the appeasement era, plus, what is that, 65 for the Jefferson War era, and then 20 for the Decatur peace era, okay? So you add all of those up, which equals, does that equal 275? And then there's 20 value points, right? 20 data points. So the N is 20, 275 divided by 20 equals 13.75%. That is the grand mean, okay? All right, so look at those 4 means again, okay, these 4 means before we touch a formula, okay, besides the grand mean formula. So we've got 27%, 11, 13, 4%. So without any protection, 27%. Pay the pirates off, 11%. Fight the pirates, 13%. Eliminate them permanently, 4%. Okay, so again, notice that the tribute mean and the war mean are close to each other. They're only 2 percentage parts. The ANOVA is going to tell us whether the 4 groups differ overall, but it will not tell us whether those 2 middle groups are distinguishable from each other. That's going to require a post hoc test. And the answer to that question is really the most important finding in this data set. So it'll tell you it'll tell you if there's some difference here, but it's not going to tell you which ones or in what direction or how many or whatever. That's not how the ANOVA works. But we do have post hoc tests, or post hoc, remember, is Latin for after the thing. Okay, so the thing in this case is the ANOVA. So we also have after the ANOVA test where we can follow up and we can get more information. So the ANOVA only gives us a certain amount of information. Then you have to gather more information with more tests later on. Sorry we can't make it simpler for you, but that's just the way statistics works. That's why it's a hard class to take. Okay, so step 0. Remember, always start with step 0 every single time. Hypotheses first. Okay, hypotheses, critical value second, and then degrees of freedom, okay, third. So never calculate until you know what you're comparing your result to. You need the finish line before you start running. So the hypothesis, you've got the null hypothesis and the alternative hypothesis, okay? So the null hypothesis is that mean 1 equals mean 2, which equals mean 3, and in this case equals mean 4, okay? Because we've got 4. All 4 policy eras produced the same average insurance rate on Mediterranean voyages. Any differences we see are simply sampling noise, okay? So we do see that there's differences, 27% versus 11%. Versus 4%, there's differences. But are they significant, or is that just noise? It's just random variation, okay? So that's what the null hypothesis says, is it's just random variation. Sure, the numbers are different, but they're not different enough that the signal outcompetes the noise. Okay? It's just noise. Alternative hypothesis is that at least one of these, if not more, are different. We're not specifying which one. We're not saying whether it's higher or lower. The ANOVA only asks, is there a real variation across these groups? Is at least one of these groups different? And then, of course, we're going to set our alpha at 0.05 because that's what we're doing in this course. Okay, and then we look at our degrees of freedom. Okay, so we have to find 2 degrees of freedom with ANOVA, right? Think of what they are. Degrees of freedom between and degrees of freedom within. Okay, now try to remember what the pause it and remember what the formula is, okay? Test yourself. So the degrees of freedom formula between is the number of groups minus 1, okay? And that, in this case, we have 4 groups. 4 minus 1 equals 3, okay? And then the degrees of freedom within are the number of observations minus the number of groups, okay? So the number of observations we have is 20, so it's the 20 different insurance rates over 5 years, okay? Minus the number of groups, which is 4 in this case. And so 20 minus 4 equals 16. All right, so degrees of freedom between is 3. Degrees of freedom within is 16. Okay, and then remember how we write this out. If you don't remember, then pause it and figure this out. Ideally, you should be doing this math along with me and pausing before I show you how to do it. You'd learn it way better. So the way we write this out is F critical, because we're finding our critical value, which is what I have up there. And then we have 316, right? That's the way we write it out. Oops, I don't know why I did it like that. At an alpha 0.05, okay? So if you look at the F table and you go, from 3 to 16, then the critical value is going to be, I guess I wrote this in the wrong order, didn't I? Is 3.24, okay? So hopefully I didn't confuse you too much by writing that in the wrong order, but that's the whole idea, okay? You're going to do your hypotheses, your degrees of freedom, and then your critical value. So 1, 2, 3. I just got ahead of myself. Okay, so that's the line. That's the finish line. If our obtained F crosses 3.24, we reject the null. If it doesn't, we retain, okay? And if that confuses you, draw it out. You should always, especially at this point, draw it out. So you've got your F distribution. You have your critical value line. In this case, our critical value is 3.24. Anything above that is rejected. Anything below it is retained, okay? So then when we get our number, we'll drop it in to wherever it is and see which side it's on. All right, 7 steps in order every time. I will not skip ahead. I will not rush, and neither should you. This is the most calculation-heavy procedure that we do in this entire course, not because the math is hard, but because there's a lot of it. So take your time. Give yourself space on the paper, please, especially for my sake when you turn things in. Check each step before moving to the next. Okay, so here's the sequence. You've got your grand mean, which we already calculated. Okay, so easy. We have our variance total, okay, our sum of squares total. So every score minus the grand mean. We want to see the difference between our scores and the grand mean, and then we square it and sum it up. And then the SS within. So every score minus its own group mean, squared and summed, right? This is the heavy one. This is the sucky one that has the most work, okay? And then we make up for that with the SS between, okay, which is just the SS total minus SS within, one subtraction, easy, okay, piece of cake. And then we have then we're going to do the mean squares, okay? We're going to standardize those 2 buckets that we have. You can do the between, MS between, and then of course the MS within. So the MS between, you're taking the SS between, divided by the degrees of freedom between, and then the same thing with the MS within. The SS within divided by the DF, the degrees of freedom within. That's your noise floor. Okay, we're going to figure out what level of noise we have in our earphones. Okay, see how noisy it is, and then we're going to compare that to the signal. Okay, and that's when we find our F value. And to get F, you're going to take your MS between. You see what we've used this one to figure out what the noise was. Now we're going to use this one to calculate what the signal is, okay? So with the F score, you're going to take the between, and you're going to divide it by the within. So the signal over the noise. So MS between is the signal, and MS within is the noise. And then for the F, you're figuring out the signal per noise, or the MS between per MS within, divided by MS within, okay? So again, steps 2 and 3 are where most of the work is. Once you have those, steps 4 through 7 are quick and easy. So every formula is building on the previous one. That's what makes it manageable. Okay, so let's go through this. So I want you guys to have one more calculation under your belt, okay, before I release you. So step 1 is the grand mean. We've already done this, okay, but you add all 20 scores. So for group 1, you have 28 plus 25 plus 27 plus 30 plus 25, which equals 135. For group 2, you have 12 plus 10 plus 11 plus 13 plus 9, which equals 55. For group 3, you have 15 plus 13 plus 14 plus 12 plus 11, which equals 65. For group 4, you have 5 plus 4 plus 4 plus 3 plus 4, which equals 20. You add all those up, which equals 275, and then you divide by the total of all of these values, right, which is 20, and as we calculated before, that equals 13.75%. So the total grand mean is 13.75% of all the groups, okay? So the 4 group means are 27, 11, 13, 4. Because all groups have an equal in of 5, then, that's a simple one. So, okay, so step 2, we're going to do, pause it, see if you can remember what it is. SS total. We want to see the gap. Remember the gap between what we observed and what we expected. So you're going to take every one of those 20 scores, subtract 13.75. So we'll just do the first group together and then pause it and do the ones on your own. So for the unprotected group, we have 28, 25, 27, 30, and 25. So then our grand mean, okay, our grand mean that we calculated here is 13.75%. So we're going to see the difference between each score and the grand mean. So minus 13.75, minus 13.75, minus 13.75, minus 13.75, minus 13.75. Okay, what does that all equal? You should technically write equal signs, but if you do it like I'm doing and be lazy, I totally understand. I'm not going to mark you down for that. I'll know what that means. For another teacher, they might mark you down for that. Just fair warning. Okay, so so what would this be? This would be 14.25, 11.25, 13.25, 16.25, and what is this last one? 11.25. Okay. Now those are all positives in this case, but again, we might get negatives, so we have to get rid of negatives. Even if the scores don't have any negatives, you still have to square it because that's just the formula. You square each of these, and then those are going to equal 203.06, 126.56, and please pause this and do the actual math before I give you everything. 175.56, 264.06, 126.56, okay? And now that we've summed it, squared it, we have to sum it, okay? You add all those up and you get 895.80, okay? So that is the sum of group 1. Now what's the next thing we have to do to get the total of all of the variance? We can't just do group 1, we have to do the other group. So this is the group 1 total. Group 2 total, I will just do this for you, is 47.80. Group 3 is 12.80. Group 4 is 477.30. Now you sum all that up, and it's 1,433.75. Okay, that is the SS total. Okay. All right, so we've got the SS total. Now we need to partition those into buckets, right? We need the within variance and the between variance. So step 3, we're going to start with the within. SS within. What is the variance between each group on its own? Okay, between the within the unprotected group, within the Jefferson group, within the Decatur group, etc. Okay, and again, this is the sucky heavy one. Okay, so slow down, don't get lost. So for every score, you're going to subtract not the grand mean. We already did that. We're going to do its own group mean because we're wanting to know what the variance is within the group. Okay, how much does just group 1 vary? How much does just group 2 vary? So we're not doing the grand mean. We're just doing the 1 group mean, group 2 group mean. Okay, so find the difference. Okay, subtract the value from the group mean, square it, sum all of the groups together, and you're good to go. Okay, so the group means we know from before, wherever it is. Okay, we did this before. I already gave it to you. Oh, I gave this to you. Okay, we didn't calculate it. I just gave it to you. Is 27, 11, 13, and 4. Okay. So here's a table of all of the calculations for you already. Okay. But what we're going to do, let me just get rid of this. We'll just go through group 1. Okay. So the group mean, not X bar bar, just X bar of group 1. Okay. Group 1 is 27. So now we need to find the variance between each score. So you have 28, you have a score of 25, you have a score of 27, you have a score of 30, and a score of 25. Okay. And then minus the group mean, which is 27, 27, 27, 27, 27. What does that equal? 28 minus 7 is 1. 25 minus 7 is negative 2. So we've got negatives again. 27 minus 27 is 0. 30 minus 27 is 3. 25 minus 27 is negative 2. Square all of those. Okay, we've got 1, positive 4 now. 0, 9, and positive 4. Okay, and then we need to add all those together. So what is that? 17. Okay. Wait, 17? 18. Yeah, I've got that 1 right there. So 17 doesn't sound right. Okay, so 18 for group 1. And then I'll just give you the totals for the rest of them. So 18 for group 1, 10 for group 2, 10 for group 3, and 2 for group 4. And then you add all of those together. So that's 20, 38, 40. Okay, so the SS within is 40. And then you have to do that for each group. Okay, so So just pause here. That the number 40 is remarkable. Okay, so compare it to SS total of 1,433.75. The within group variable is 40 out of 1,400. So it's less than 3% of the total variance. That's not a lot of variance within each group. And why was it so low? It was so low because insurance rates within each era were very stable. Insurance companies know how to set insurance rates. They know how to assess for risk and how dangerous things were. Okay, so there wasn't a lot of variation. Insurance is not like politics. When you're dealing with real money and real consequences and real risk, which politicians usually aren't, then things are done right. Okay, so insurance company rates were very stable. Once the 1795 treaty was signed, Mediterranean rates settled to around 11% under Jefferson and stayed there. Once Decatur's peace held, rates fell to 4% and stayed there. So these are not chaotic year-to-year numbers. They are market assessments of a stable risk environment within each era. So that noise floor of 40, that's almost nothing. Okay, so the signal is going to be overwhelming. Okay, you can already see with that 40 being only 3%, we're going to have a high F rate value. All right, step 4. So we did the SS within. Now we need to go see what's going on between our two buckets. Okay. So how do we do this? This is the easy one. This makes up for the last step. This is just the simple subtraction thing. So SS between is the total, the SS total minus the SS within. Okay, easy. So the SS total was 1,433.75. Okay, 1433.75, and the SS within was 40. Remember. So the between variance is going to be a large number, okay? And that is 1,393.75, okay? And you can easily verify that because if you go the other way, 1,903.75 plus 40 will equal the total, okay? It's very obvious math. 1 plus 1 equals, okay, 50% of something, 50% of something equals 100%, okay? Or in this case, was 3% of something plus 97% of something equals 100% of the total. The total is 100%. If that doesn't make sense, just ignore what I said. It's okay. As long as you remember the formula. All right, so 1,393 out of 1,400 units of variance is, sitting between groups, not within. That's 97.2%. So before you've even calculated F, the story is already visible. The groups are dramatically different from each other. Okay, so this is the noise floor. This is the signal. Okay, before we've standardized it and everything, but you can still see that there's a huge difference between those two. So now we're going to standardize it just to make sure. Okay, you got to be able to compare apples and apples, not apples and oranges. So step 5, we're going to standardize it by making it the percentage interest rates per each degree of freedom. Okay, so you're going to divide each sum of squares by its degrees of freedom. So we'll start with between. So the mean of squares between equals the SS between, which we just calculated, divided by the degrees of freedom between, which we calculated in step 0. So the SS between, which we have right here, is 1,393.75 divided by the degrees of freedom between, which we calculated. Where did we calculate it? Way up here. Okay, so degrees of freedom between is 3. Degrees of freedom within was 16. We'll just keep that in mind so we don't have to go through all these pages. Come on, you can do it. I believe in you. Thank you. Degrees of freedom between was 3, I believe. Did I do that right? Yes. Yeah, 3 and 16. Okay, so degrees of freedom between was 3, which equals 464.58. That's the MS between. And then we'll do the same thing with MS within, but we're going to use all the within things, of course. So that is the SS within. I don't know why I made that line so big, but the SS within divided by degrees of freedom within. So SS within is 40. Divided by degrees of freedom within, which was 16. So this is going to be very small, equals 2.5. Okay, so degrees of the mean of squares between, the mean of squares within. Okay, which then brings us to step 7. Okay, which is really simple. Step 7, finding the F value. So the F value equals the signal over the noise. Okay, so What is the signal? Do you guys remember which one of these is the signal? Pause it and try to think about this before you hear the answer. The signal is the mean of squares between, okay, over the mean of squares within, okay? And we know that the between was 464.58 and the mean of squares within was 2.5. So that equals out to 185.83, okay? 185.83 is our F value, which, like we suspected, is enormous. If we go back to our distribution, if I can get it to cooperate, okay, our critical value is 3.24, and we have our F value is 185.83. You think we're going to reject the null hypothesis? Yeah, I mean, that is off the charts high. It's so obvious that going to war, and especially Decatur bringing us peace, was such a huge difference between when we had pirates and we were unprotected and when we were protected, okay? It's huge, okay? So an F value of 185.83 is 57 times the critical value. So the F distribution goes from 0 to maybe 10, okay, as it flattens out. An F of 185 doesn't even land on that curve. It's off the page. It's off the charts. The tail that's supposed to extend indefinitely to the right, our value is out there somewhere. Like, I mean, if you drew it like this, right, then maybe you have 185.83 way out here, okay? It doesn't even land on the curve. And there's essentially nothing between our result and zero probability under the null. It's so obviously clear that not negotiating with terrorists is the right thing to do. At least if you're talking about Barbary Coast pirates, that's for sure. Okay, and at least if you're using the variables that we're using. So the decision, let me go back. I'm pretty sure we know what the decision is. That's the last step. We're going to absolutely reject the null, okay? So how we would write this out is an F value, an F critical at 316 at the, 316, the location of 316 is equal to 185.83, okay, with a p-value of, in our class we're just doing less than 0.05, but I guarantee that's less than 0.001, okay, maybe even 0.001. And then we haven't got into this, but this right here, it's not an in, it's an eta squared, okay? So the eta squared is 0.972. So we're going to talk about that next, okay? So what that means is 97% of the total variance in what it costs American merchants to insure a Mediterranean voyage is explained by which policy error their voyage fell into. This is the effect size. Okay, that's not a modest result. That's not a result that kind of squeaks past the critical value. That's a result that says policy error is nearly the entire story of how risky ship voyages were to the Mediterranean, at least insurance policy-wise. Okay, so the way we would say this in APA format would be something like, one-way ANOVA revealed a significant effect of diplomatic policy error on Mediterranean marine insurance rates. F316 equals 185.83 with a p less than 0.001 and an eta squared of 0.972. So policy error accounted for 97.2% of the total variance in insurance rates. Okay, so now let's talk about eta squared. Okay, so it's not an in, it's an eta. So eta squared is really easy to calculate. Eta squared equals the sum of squares between over the sum of squares total. Okay, so the SS between is the, let's do this way, the variation, okay, explained by the groups. But there's differences between the groups. And the SS total is all the variation, both between and within the groups. Okay. So eta squared tells you what proportion of the total variability is explained by the independent variable. And the SS is the variability between the two independent variables. So imagine all your scores are spread out from each other, right? That spread is what we call variability. ANOVA asks, why are the scores spread out? So there are two main possibilities. One, because the groups are genuinely different. The independent variable caused the differences. Or two, because things naturally vary anyways. You know, there's random differences, noise, chance, whatever. Eta squared tells you how much of the total spread comes from number one, from the independent variable. So this is the key idea behind ANOVA and effect size, right? And this whole topic we're dealing with here is effect size. Eta squared is the effect size. So the important thing is SS between is defined as the variability created by differences between the group means. And the group means differ because the independent variable created the group. So when you divide, okay, SS between over SS total, you're asking what fraction of all variability comes from differences between the groups that were created by the independent variable. Okay, so for example, suppose the independent variable is your teaching method and the dependent variable is exam scores. You split people into method A, B, and C. And then like imagine the group averages are 70, 80, 90. Those averages are pretty far apart. So ANOVA says the separation between the means is variability due to group membership. Those groups were defined by the independent variable, by the teaching method. They were created by using different teaching methods. So the variability among those means is attributed to the teaching method. It's attributed to the independent variable. That's exactly what SS between measures. Okay. Meanwhile, inside the group, people still different. One student gets 72, another gets 65, another gets 77. Those differences are not explained by the teaching method because those students had the same method. So that leftover spread becomes the SS within, which is treated as, unexplained random variation. Okay. So mathematically, we know that SS total equals the SS between plus the SS within, right? So SS between is attributed to the independent variable, and SS within is not attributable to the independent variable. So then eta square asks, out of all the variation that exists, how much comes from the variation that the independent variable created? How much comes from the variation between the independent variable groups? Teaching method A, teaching method B, teaching method C. Okay. And one subtle but important point is that eta squared does not prove causation by itself. This comes after you do the ANOVA. It measures how strongly the variability is associated with the independent variable defined groups. Okay, you can only interpret it causally if the study design justifies causation. So like a proper experiment with random assignment. Okay. But that's just a side point. So in our example, let's just go through this a little bit again, specifically with our example. Our independent variable is the policy, right, used against the Barbary pirates. So unprotected, Adams' appeasement, tributes, Jefferson's war, Decatur's enforced peace. And the dependent variable is the insurance rates. Okay, that say how risky everything was. No, insurance rates. I meant to say rates. Basically the same thing, okay? So ANOVA is asking, in our experiment, how much of the variation in insurance rates is connected to the policy period that the ships were in, okay? And so we know with our averages, we have group 1, 2, 3, 4. It was, if I remember right, 27, 11, 13, and 4. Okay, so those group means are different from each other. And that spread, those differences, the variability between the groups, okay, all the variability between, that variability becomes the SS between. We measure it using the SS between. It's the variability between the groups, okay? Because the groups themselves were created by the independent variable. Okay, so SS between, since these are the independent variables, right? SS between measures the variability in insurance rates associated with policy differences. It measures the variability in the independent variables because the insurance rates are the independent variables, okay? But within each group, the insurance rates are still going to vary a little bit. There's some voyages are riskier, there's different cargo, the weather's different, the ship quality, the route differences, whatever. And that leftover variability within each group is the SS within. Okay, just a reminder of how this works because it exists within the same policy condition. So then if we go back to the eta squared, okay, so then eta squared, which is SS, let's get that arrow out of the way so it doesn't confuse you, SS between over SS total, it tells you what proportion of all variation in the insurance rates it was associated with differences amongst the piracy policies. Okay, so what variation is associated with those differences? So let's see what the SS between and total was. Where do we have that? SS between was 1393.75. Okay, 1393.75 over the SS total, which was 1433.75. Okay, and so that's how we got our eta squared, okay, which was, what was that, 97 equals 0.972, okay, 0.972. So again, that means that 97.2% of the variability in the insurance rates is because of the piracy policy that was in effect at the time, okay, which would suggest that policy choice had a very strong relationship with insurance costs. Now, notice the wording carefully. We say associated with, okay? The insurance rates are strongly associated with the anti-piracy policy. And that distinction matters because ANOVA itself only partitions variation. It does not automatically prove historical causation. We're just saying they're associated, they're correlated, they're not it's not causational. Okay? You guys should really understand that at this point with all your statistics classes. Okay? So we have our eta squared. Eta squared equals 0.972. Now we remember Cohen's guidelines. Okay, so all these are, it's simply saying that an eta squared of x such number means that it's a small relationship, a strong one, whatever. It's just a guideline. So Cohen said that a 0.01 is small. Okay, a 0.06 is medium. A 0.14 is large. Okay, ours is way down here at 0.972. Okay, there's no category for that. It's simply overwhelming. So, and this shouldn't surprise us at this point, right? We deliberately chose a dependent variable, insurance rates, that directly measures what these policies were trying to control, the cost and predictability of the Mediterranean trade. And we have 4 distinct policy areas that span from zero naval protection to total exposure to permanent military dominance. The treatment variation is extreme and the measurement is precise. So, of course, the effect size is going to be enormous. It really shouldn't surprise us. Although people argued about it at the time, right? Thomas Jefferson had to run an entire presidential campaign in order to implement his policy. And to many people, it wasn't obvious that going to war or total dominance would be better than nothing. They might have thought going to war would make things even worse. Okay, so even though it's obvious from hindsight, it's not necessarily obvious while it's going on. Okay? And you might have guessed that appeasement and paying tribute would have been less effective than Thomas Jefferson's war campaign, and turns out it wasn't. It was about the same. Okay, so in messier observational research, studying the effect of a brief intervention like on mood or income or health outcomes, you would expect much smaller effect sizes because many factors are at play. An eta squared of 0.14 would be impressive. A 0.97 would be extraordinary. So what we have here is possible because we have the right dependent variable for the question. Okay, so you have, in this case, you have an F of 185.83. You definitely rejected the null hypothesis. You know the 4 policy eras produce significantly different insurance rates. But that's not enough. So the F ratio is what we call, I talked about this before, but it's called an omnibus test, right? Omnibus means everything. It tells you that somewhere across these 4 groups, something is different. It does not tell you which groups differ from which. It does not tell you whether the unprotected era was significantly worse than the tribute era. It does not tell you whether Jefferson's war produce different results than the tribute error. It doesn't, even though it's 11% and 13%, it doesn't tell you if those two are significantly different. Or whether in the eyes of insurance underwriters, paying the pirates and fighting them were essentially the same thing. So that last question is the most important one in this data set. Look at the group means again, right? So you have the tribute era was 11% underwriting risk, and the Jefferson war era, oops, that's... Sorry for Jewish, I didn't mean to do that. Okay, we'll just write Jeff there. With good old Jeffy Boys era, it was 13% underwriter risk. 2 percentage points apart, right? The F ratio is 185, but that enormous F value is driven mostly by the gap between the unprotected era and everything else. The question of whether tribute and war differed from each other is a different question entirely. Okay? And the omnibus F is not designed to answer it. To answer that question, you need good old post hoc test. So a post hoc test is a procedure that compares every possible pair of group means at the same time. Okay? Not like a t-test where you do 1 and then 1 and then 1 and then 1. So it compares them simultaneously, all at the same time, while controlling for the probability of false positives across all of the comparisons, again, at the same time. So that procedure, it's basically a t-test, but a t-test where everything's being done at once and controlling purposefully for the false positives that could come up. So we call that a Tukey test, okay, or Tukey's. It's kind of funny, but Tukey's honestly significant difference. I've always thought that was sort of a funny name. It sounds like an early 1900s like circus show act or something. Come see Tukey's honestly significant difference. So anyhow, when we run it later in our next video in part C, you're going to find something that at least surprised me when I first saw it in this data. The insurance market, the people who had the money on the line, the underwriters writing policies in Philadelphia and Boston and New York, they couldn't statistically distinguish between paying the Barbary pirates and fighting them. So tribute and war produced the same insurance rates. Both cut the premium from 27% to roughly 11 to 13%, and both worked. The form of the policy did not matter to the underwriters. Okay? What mattered was something else entirely. And if that's true, if tribute and war were statistically identical in their effect on the Mediterranean trade risk, then what exactly was Jefferson arguing about? What was he running on? So the data can't answer that question on its own, but it can tell you what the answer is not, and that forces a more careful question. What is the difference between two policies that produce the same short-term outcome? Right. So next lecture, we're going to do Tukey's honestly significant difference with 6 comparisons. And yeah, hopefully you guys are enjoying this. I like to do these sort of weird stories because they're messy. Most statistics classes just give you very simple cut and dry things so that you can easily understand it, but it doesn't give you the true story of doing statistics, which is that statistics are messy. Variables are messy. There's things that are constantly interfering and making it difficult to run the right statistics and interpret the right statistics and choose the right variable in the first place to do the statistics. And so using these historical stories, I think, really illustrates it in a much more honest way than how statistics is normally taught. And I hope that you also find it a bit more interesting too than just dry, boring math. All right, see you in the next lecture.